Right, so I'll tell you about two ways to create strongly interacting Fermi gases that, of course, you're all very familiar with. One is if you happen to have a scattering resonance, then you can use that to induce strong interactions in the gas. Or you actually quench the role of kinetic energy by taking your atoms and putting them into an optical lattice, and thereby promote the role of interaction. So these are two ways that you can use, and we'll see what happens when you do this. First, in the case of this strong scattering resonance, you can explore the BEC-BCS crossover in these Fermi gases. You can go from a regime where you have tightly bound molecules, which form a Bose-Einstein condensate, all the way to the case of a long-range Cooper pairing in the BCS state. And it's just by tuning a knob in the lab, which is your magnetic field. So it's quite a gift of nature to allow us to see these systems. And for a while now, we know that these gases are superfluid by observing vortices upon rotation. You could ask what is actually in particular super about these gases. And if you think a bit, it's actually the role of heat transport. Tisha and Landau came up with their two-fluid model. In fact, there's some Russians in the audience. I think Tisha was a few years earlier, 1938. But let's not get into that. And once you have two fluids, the superfluid and the normal gas, you get two sound modes. And this is the first sound mode, which is just the density sound with which we talk to each other. And the second sound is the wave-like propagation of heat in the system. Famously demonstrated in helium by Peshkov in 1944 and in unitary Fermi gases by Rudi Grimm's group in 2013. They used a density probe, but we felt like it would be so wonderful to see the heat directly. So how can you actually have a heat thermometer? So this is actually a general technique that works for any of your systems if you have any sort of spectrum that depends on temperature. The moment you have something that depends on temperature, great, you can use it to measure heat transport. It sounds very obvious as I say, but it's actually a good thing to have sink in. So in our cases, we have a radio frequency spectrum that depends on temperature. Simply, without interactions, I know with atomic clock precision what energy I have to put into my gas to flip a spin from one spin state to the other. Fine. But if I have interactions, for example, if I have pairing, I need to provide more energy to first break the pair and then be able to promote the loose particle into the third state, into another empty state. That's why at low temperatures you get a shift of the spectrum. But honestly speaking, I don't even need to know why certain things shift. I only need that there is a spectrum that shifts in temperature. And that way you can actually have a thermometer by just sitting at a particular frequency where you like to be sensitive. And you have a hot spectrum that gives you a large count here, medium temperature, and a cold spectrum. And you get a more or less linear, doesn't even have to be linear, but roughly linear signal versus temperature that you can use to probe your system. Again, in a cartoon picture, which I don't have to have, you can have the idea that what we are doing, if you sit away from this shifted peak, we are only talking to the unpaired loners, if you want, those that have not yet found the pair. We transfer those, giving us a signal directly of the gas of excitations, which is heat. Eugene.
What's the resolution in temperature?
Beautiful. Thanks for the question. If we apply this on our gas, by the way, the gas is trapped in a box potential, as we saw in Henning's talk yesterday. The density looks relatively boring, as you can see, but in the temperature, if you have a gradient in temperature, you see a gradient. And now let's look at the resolution. This is nanokelvin, and so you can actually, with sub-nanokelvin precision, say what the local temperature is. So it's actually quite sharp.
Can you do it at a few percent level? Basically, how much do you have to distort the temperatures?
Few percent, yeah. So here there is an amplitude which is a few percent. In fact, if you go to 5 or 10%, we get nonlinear stuff happening, which is itself very interesting. But we make sure that we are in the linear response with this heat probe and checked it. So just a few percent increase in the temperature on one side of the box versus the other, we can see that. Yeah. Yes.
So the modulator is local. So yeah, so we know for the static quantity, such as equilibrium state, we can use the local density approximation. But here, you consider RF spectroscopy, so it's a dynamical quantity. So can we still use the local density approximation for the dynamical quantity?
Since I'm an experimentalist, I don't have to use local density approximation. I can just do the experiment, which is fantastic. But what you say more seriously, answering to your question, is what is going on locally? What's the local resolution? So this is local because we do the RF flip and immediately take a picture. But of course, the RF pulse takes a certain time. So there's actually a little bit of diffusion of the signal during the pulse time. So which actually lowers the resolution away from the optical resolution and to something that's more like on the order of maybe 10 microns in this box. So basically 1/10 of this box, which is about 10 interparticle spacings. So that's our resolution just from this sort of diffusion effect. And you could say it's complete. I mean, local density approximation will be super fine because this is even much larger than the interparticle spacing. But we don't actually use, you will see, we don't actually use any sort of local density. We just look at the wave now. It's very, it is very simple. It becomes like an undergraduate experiment where you see something sloshing back and forth, but with the difference from probably the undergraduate experiment that that's not the density, but it's the heat that's propagating. And you see it slosh back and forth. So these are the frames from the movie as a function of time. You see heat slosh back and forth in your system. And it's kind of slow, like a couple of 100 milliseconds for this sound wave. Yeah. The button.
So you mentioned that the R spectra depends on temperature, and then you set at a particular frequency.
Yeah.
Is it easy to then use that amplitude to get the precise temperature? Because you had plots in real temperatures, not arbitrary.
Beautiful. That is the hardest part, which took, I don't want to say how long, but to calibrate your thermometer, that's tough stuff. And you need to make sure you understand everything. If you just want to see a heat wave, you don't have to calibrate. You can just use it and just watch it go perfect. So if you're interested just in the speed of second sound, no problem. You don't need to calibrate your thermometer. But if you also want the quantitative response function, as you wiggle temperature, what's the response in density, or vice versa, which we were after, you will need to calibrate in absolute terms, and that is difficult, and you spend most of your time doing that. Yeah. Yeah. So actually, in this paper, you will find the response functions for the density and the density temperature response directly from these data. Yeah.
So Martin, I just want to understand a little better the connection between the movie and the curve here.
Yeah.
So this is fixing a position and looking at a function of time.
Over there. Yeah. So this is the movie. You see, it's a sloshing mode back and forth. It's the lowest second sound mode in this box, going back and forth. And so you integrate over the. Oops, that is great. I didn't know it was live. It's actually a live being. You can integrate over the boring direction and get the strip, which looks blue-red in the beginning. Okay, and then you plot these strips versus time, and it turns like red-blue, and then blue-red, and so. And here, what you do is you extract the lowest Fourier mode, if you want to say it in a fancy way, of this sloshing mode. You just plot the amplitude of that mode versus time. Yeah. Right, and then now you can actually go through the transition and see what is so super about a superfluid. Above TC, you have boring, sort of not boring, I don't know, like exponential decay, just a decay of your local hotspot in time, whereas if you go below TC, you start seeing a ringing. So you see second sound, the wave-like propagation of heat in the gas. And it looks quite nice, and you can actually basically directly tell now, oh, yes, here we are super, here we are normal, which is nice. This is sort of a prelude to the main part of the talk, just saying like there are systems where we have actually superfluids, and they are coming very close to this to the BEC critical temperature line, which is in this Umura plot. We talked about it yesterday. Of course, in order to put lithium-6 and potassium-40 on this graph, the authors of this paper, which is Pablo Carrillo Herrero, they had to scale the numbers by 10 to the 8. But yeah, so that's not, okay. So it's basically an interesting story that cold atoms provide the strongest coupling fermionic superfluid. Now, let us make closer connection to Conrad's method and actually switch on the lattice and study therefore the Hubbard model. I'm in this beautiful situation that I don't have to introduce the Hubbard model because we had wonderful talks before. And it's a very interesting time because we are starting to see rather significant improvements in the precision of cold atom simulators, but also, once the theorists notice that there is experiments that could actually go to lower temperatures, they beat you and go to 10 times lower even. So it's quite amazing actually what is also happening on the theoretical front to understand this model. And it seems like at the moment that the plain vanilla Hubbard model is not enough to explain high TC superconductivity. So we need to probably in the future attach bells and whistles and see what the role of those extra terms are. But it's already fascinating to just understand this model, and there has been, of course, a flurry of activities. I just flashed these. I don't want to go through just of the cold atom works, and I will tell you about our recent result on fermion pairing, sort of making contact to the first part of the talk. Just to introduce our experiment, a while ago we were able to image the total density instead of having these parity projected images. So we were able to see the doublons and the singlons in one picture, which was nice, because then you can actually plot your density as a function of potential and obtain the entire equation of state. What you're seeing here is how a strongly correlated sort of liquid turns into a band and a Mott insulator for strong interactions. This is all happening in a trap, as you can see, because in the center you have a high density, so 2 atoms per side, and then here you end up with a Mott insulator, 1 atoms per side. And this gas, even though you might think it looks thermal, it's not thermal, it's strongly correlated, just the atoms can hop around much more freely than over there with the large U. And so from these pictures you can get a wealth of information. You can, as I mentioned, get the equation of state, just plot the density versus potential, integrate to get the pressure, and take the derivative to get the compressibility, giving you a measure of the equation of state. But microscopically also, it's very fascinating. First, you can check that you have fermions. It's a good thing to check. You should see that among the like fermions, say all the spin-ups, whenever you find a spin-up over here, there is a Pauli or exchange hole surrounding that spin-up, just because of the Pauli principle. And also, if you look at the total density, you always see these doublon hole pairs, like there's a doublon next to a hole, doublon next to a hole. Of course, that's just a single image, but you can repeat, and do statistics and observe indeed these doublon hole correlations to be very frequent. That's precisely what you expect when you have a Mott insulator with spin up and spin down next to each other, and sometimes the ups hop on top of the downs, or more professionally speaking, these doublon holes are an admixture of the wave function, even in the ground state. And you can directly see this. And to combine the two, you can actually use the local fluctuations, the density fluctuations, and the measured compressibility to obtain temperature from the fluctuation dissipation theorem. So this is quite powerful to see these atoms with single resolution. But now this talk will be about the attractive Hubbard model. In fact, the story for low filling is very similar to what I started with. There's again going to be a BC-BCS crossover. Simply for strong attraction, you will form these doublons, these happy local bosons, which should form a Bose-Einstein condensate. Whereas if you have weak attraction, again, you should see a Bardeen-Cooper-Schrieffer-like state with very small binding, so you have to cool a lot to be able to pair these guys up. But in the middle, for intermediate interactions, there is already a region where these pairs form, but they're not yet coherent. So sometimes that's called a pseudo-gap phase. It's going to be interesting to see whether we can see these sort of pairs. Over here, I remind you of the wonderful mapping that exists between the repulsive Hubbard model and the attractive Hubbard model. It's a very simple mapping where you do a partial particle hole transformation. The blues are just turned into holes, and the reds, they stay put where they are. And so when you have a site on the repulsive side where there's a single blue atom, it becomes a hole. Whereas if you have a site that's a single red atom, it becomes a doublon under this transformation. And this is actually a beautiful picture from a paper by Thierry, reminding everyone of this mapping, that, for example, the interferomagnetic state, which is maybe nicest to look at, turns into charge density wave, where you have doublon hole, doublon hole. And this works for every state, of course. So also if you happen to have found a doped interferomagnetic mod insulator that might even have a D-wave superfluid state, who knows, that state will also map onto the attractive Hubbard model, where you will expect something like a charge density wave with interesting things happening for the loners in between this charge density wave. So now to see this, we really want to see spin. So what we do is we actually take our single Fermi Hubbard system and we split it into two in a bilayer. In this case, in the vertical direction. The splitting is only half a micron, but we can make sure that the imaging has a node of the imaging light on one layer and not on the other if you want to image spin up. And we just flip to image spin down, and we get, therefore, the total information of spin and density. So we get these digitized images which have all these blues and reds sprinkled in, and the white dots are the doublons. So then we can look at what happens as you increase the interaction strength. This is a picture of a non-interacting Fermi gas, where just by chance some atoms happen to be on top of each other. And now as you increase the interaction strength, pairs form, and they even start to order. I would say by eye you already see there's some tendency for this charge density wave to form in some regions. In others instead you see it's completely the opposite of a charge density wave. That will be actually a dual. I didn't talk about this, but that's actually hidden underneath that is a superfluid fluctuation. So charge density wave and superfluid fluctuations go hand in hand. So now when we orient ourselves again on this phase diagram, this is temperature versus interaction strength. This would be the BEC-BCS crossover. We would love to be in the superfluid phase here as well. We are not. Don't ask me why. We're a little bit hotter. And the experiments are scanning through in this white region above TC, but in the regime where there's already interesting correlations going on. So let's see whether we see some glimpse of this pairing. First, for strong attraction, we see lots and lots of these doublons. Of course, we're not surprised. These guys really would like to be on top of each other. But every once in a while, you, of course, see some singlons in there. And very often, actually, you will see a spin up is neighboring a spin down very tightly. You also see we have a little bit of spin imbalance in this picture. So that is expected. These are just the fact that, again, in the ground state of this pair, it's not the perfect doublon. It, of course, has an admixture of a up-down fluctuation where, say, the spin-up atom migrates onto the next site, but it'll come back eventually. So you will expect these singlon fluctuations just in the same way that you expected the doublon hole fluctuations on the repulsive side. I already talked about these local patches of charge density wave order, which are nice to see. Now, if you weaken the attraction, it starts to look like a soup, like some mess, right? You don't know, are they still paired or not? You can still have fun and with a cartoon-like thing, like try to guess who might be paired to whom. But this is, of course, just a cartoon image. How do we know? Well, we will just have to do spin correlations. We will have to ask, is there for every spin-up atom a spin-down atom somewhere in the neighborhood? Then that's a pair, or not. So already without any interaction, you get, of course, interesting correlations, but these come just from the like pairs, the spin-ups with the spin-ups and the spin-downs with the spin-downs. That's the Pauli hole, which you can extract from these images. If you now switch on attraction, you see this correlation hole seems to increase and increase even further for intermediate interaction strength. This is a combination now of what we had before at 0 interactions, the Pauli hole, and most dominantly here, the attraction between spin up and spin down, making sure that whenever there's a spin up atom, it's much more likely to find a spin down on the neighboring sites instead of another spin up. And here in this regime of very strong interactions, you see it becomes a very local correlation where at most you will find a spin down next to the spin up, and it will only be on the neighboring site. It will not be able to migrate far. It will not be correlated much. So it's a very local pair here. So now you can just take the sum of this correlator that gives you the total magnetization fluctuation, and you can ask when is that non-zero, when is that 0, and you see at some interaction strength for our temperatures, you get that this total magnetization fluctuation drops to 0. You remember that this is related to the spin susceptibility. So if it drops to 0, that means you have a pairing gap. You have a gap to break these pairs if you were to apply a difference in chemical potentials. Like in the case of electrons, you would apply a magnetic field and try to break the pairs. And that would not be easy once you go beyond U over T of 6-ish for our temperatures. This is not a critical interaction strength or anything. It's just like at our temperature, that's roughly where you see the e to the minus interaction strength over temperature going to pretty much 0. So we say like, great, over here we have a paired gas, but it's actually a gas of non-local pairs. If you look at the images, you see a lot of these loners nearby, and there's actually quite a length out beyond the interparticle spacing where you still have these correlations. So the pairing is a many-body affair. It's not a two-body affair. The interparticle spacing would be this dashed line, slightly smaller than one site, because we have slightly smaller than half filling here, and the correlations extend beyond that. Just as a glimpse of fun stuff happening in the lab right now, we actually wiggled the interaction strength just by wiggling the magnetic field and just try to see, can we break up these pairs? And turns out we can break them up. So for small interaction strength, you break them up at earlier, at lower frequencies, and then as you increase the interaction strength, you go to higher frequencies, and then you can sort of get a peak position versus U over T that resembles quite closely what you expect for the binding energy of these pairs. You do see, of course, these spectra are quite broad on the order of the bandwidth, so that's what you get. It's actually a whole bunch of states that contributes here. Yeah.
Can you go back to your image? You said that you were seeing superfluid fluctuations in the. Please. You said we were seeing in your original image superfluid fluctuations in the part that weren't checkerboard spin density waves. So now that we've seen the correlator, can you say, with your trained eye, if you go back to that original image, which had patches of,
for example,
yeah.
Like,
so you're saying that is a. Why would you say that's a superfluid fluctuation?
By just looking at it, I don't know. But so I have to put in a little bit what I know. I think I should tell you the story. This is actually beautiful. So in the repulsive Hubbard model, you know about the Z, X, and Y interferometers as possible states. So it's actually, they're smoothly connected, right? You can rotate in 3D this order parameter around. It's all the same phase. And at half, in a spin-balanced gas and without magnetization at all, like they're all completely the same. Now, if you go to the attractive side of things, also at half filling, you will find that the Z interferometer maps onto the charge density wave, and the XY interferometer maps onto the superfluid phase. It's actually very fun to do the mapping in your head. The X interferometer, for example, is spin up plus spin down on a given site. But that means under this mapping, you get that maps onto double on plus hole on a single site. So it's beautiful. There's a phase that's important between those two, and it's beautiful. Everywhere you have the same. If you had a ground state superfluid with that phase, everywhere they would have the same superposition of double on and hole on each site. And so that's your phase stiffness. Fantastic. You have a superfluid. Right, and you also see the particle number is not defined, as it should be when you have your defined phase. So if you take an image, it'll look completely random in terms of the density, and not ordered. So anything that's not ordered, I can claim a little bit, that's not the charge density wave, so it's probably the other stuff. Now, of course, it could also be just thermal. But there is now a thing, like at half filling, charge density wave and superfluid order have exactly the same sort of, they're degenerate, just like XYZ antiferromagnetic are the same. But as you go to lower filling, away from half filling, that corresponds to applying a magnetic field on the repulsive Hubbard model, which quenches, as actually Wasim has shown experimentally, which quenches the Z antiferromagnetic and promotes XY antiferromagnetic order. And for us, it means the superfluid will win out over the charge density wave. So if you work at 80% filling, and we see a certain charge density wave correlation, we know that the superfluid correlations must be stronger than that.
I see. Yeah. Right.
Yeah. So,
Coming back to this, right? The scale at which the preform pairs appear.
Yeah.
Right? Can you actually quantify that as a function for different values of U? Can you see that there is an onset where pairs form, which is larger and larger as U is larger and larger?
Yeah. So yes. Honestly, it's a lot of data, so we were a bit lazy by tweaking the simplest knob in the lab, which was interaction strength and not temperature. What we should do to do what you propose is to, for every U, we also do it versus temperature.
For a few, yeah.
For a few temperatures, and it's a lot of data, and so I think where's Bhutan? You do it, okay? So let me tell you, we actually found a new way to have a quicker way to obtain these charge density waves. But I couldn't put it in the talk, it was already too long. But there's a nice way to suddenly glue the pairs together into a doublon so that you don't have to take all these charge correlations. Okay. And so now you can take the measure of these doublons as a measure of pairing. And so we think we can be much faster in the data taking and therefore now more easily scan temperature and not grow old. Okay. It's him doing it, Bhutan here in the audience. Yeah? It's not spatial because we can locally resolve that it's not spatial. So we check that. I'm sure it can be temperature, but it's actually very tricky. So actually, I had some fun, to play with the plaquette. If you allow me, like that's apparently the simplest, the only thing I can do. Fermi Hubbard plaquette, you already get a bunch of states that are very close in energy, whose spectra already give you a width on the order of a bunch of T, like T, 2T, something like that. Already, if you're very cold, on the order of T squared over U temperatures, you still get something that's kind of broad. So yes, it can be temperature, but it's tough. It's tough to be colder. Yeah. So yeah. I'll well, it's all subtracted from the question time, right? Super. Okay, so I jump ahead. This is just to look at the density correlations. We already saw the checkerboard. Now this is the correlator, and it's fairly long ranged. It's okay. Gives you a nice peak in Fourier space. Simply saying there's a good checkerboard correlations, and it's quite nice to look at the correlator versus momentum, and you see a sharp peak. The black line, that's the non-interacting gas, and the red line is the interacting gas at the peak. We also saw, and luckily I don't have to introduce that much, polarons in this gas. Actually, that's the mapped version of the repulsive magnetic polaron by Christian and Emmanuel. So what happens here is that one synglon decides to go on a march, leaving behind a string. And the same would happen also in the superfluid case, where a synglon moves around and leaves behind a string of flipped superfluid phase. It's kind of cute. Of course, we cannot see the superfluid, we can only see the charge density wave and map out what is the range of this damage that's been done by this impurity. And we get a certain idea of the size of this polaron in direct analogy to the repulsive magnetic polaron. So that's basically the story of the balanced gas. Here, these are the phases of the Hubbard model. Under the microscope, we have seen the attractive and the repulsive gas. We've seen the pair fluctuations up, down, and the double on hole fluctuations, which are actually mapped versions of each other. So now, let's open up one more axis, which is switching on magnetization. More spin-ups than spin-downs. That connects to the doped Hubbard model. You expect phases similarly to the doped Hubbard model, or the mapped versions of it. This is sort of a cartoon attempt at a phase diagram. We don't know what's going to happen, but there's certainly an interesting type of superfluid lurking. Well, certainly I shouldn't say, but like it's expected that there is a FFLO type order, full de Ferrell-Lakanov-Chinikov type superfluid, where in momentum space, the Cooper pairs now have finite momentum. In real space, you would actually start to see that the excess fermions are forming a lattice. So it's quite interesting. And if there is something like a D-wave superfluid on the repulsive side, there would also be some sort of D-wave interferominate on the attractive side. So who knows what will happen? We should do the experiment. And what we have access to in these images at the moment, what we're analyzing is, do we have charge density wave correlations? That's sort of a proxy for superfluid correlations, which you cannot see. What does the excess fermion population do? Is it a Fermi liquid, or what's going on? And see how we go from the spin balanced gas of like just pairs to a spin imbalanced Bose-Fermi mixture, if you want. It's actually a hardcore Bose-Fermi mixture, and it's quite interesting to look at. So this is the spin balanced gas that we now imbalance, and you see you get more blues than reds. And what we have here is then a Fermi C, if you want, doped with bosons. So Bose-Fermi mixture. So let's just see what we can extract from there. We can first of all, of course, get the spin density profiles in our trap. And this is the balanced case. You see spin up and spin down are on top of each other. And here you see the splitting. And for strong imbalance, the spin ups do their own thing. They have a Fermi C. There are Fermi C on top of the paired gas. You see that it's basically paired because the spin down density is pretty much equal to the double on density. Yes?
What's your U?
Say again?
What's your U?
Tunable. You probably ask what the U is for this picture. Let me guess, 6. Okay. I should make a note to always have in the upper right corner what U it is. It's a typical U. Okay. Right. We can also look at the Singlon density. There are Singlons already in the balanced gas. We talked about this. That's the non-local nature of the pairs. And those then split. And over here you have almost no spin-down Singlons. And, of course, a lot of spin-up excess fermions. And we can ask whether these excess fermions form a Fermi C, etc. But to sort of not overwhelm you, I'll just focus on 2 correlators. One is the double-on correlator, which is sort of asking, do these bosons avoid at one interparticle spacing distance? Because we are interested in seeing, are these bosons hardcore repulsive on the next neighbor, as we expect? And yes, they are. They don't want to be near each other. And that's actually a consequence of Pauli blocking, because these bosons are non-local. So these guys, if they're neighboring, that's not so nice, because this guy can no longer spread its wings to the right side. So it cannot no longer have a spin down fluctuating to the right. So they would like to stay apart from each other. And so there's always a negative correlation, no matter what the imbalance is. The different colors are the imbalance. It gets, you can also ask, what about the correlation between these doublons and the excess singlons? There you are asking, do also these fermions, these excess fermions, do they get repelled from the bosons? They should, you would say, because if I have an excess fermion of spin up on one side, you should also make the pair unhappy, because it can no longer tunnel over there with its own blue atom to the right. So you would expect that they should repel. But as you increase magnetization, at some point, beautifully, you see like they stop repelling, interestingly, and cross to 0. And you can actually have an intuition if you go to the extreme imbalance, which we didn't quite achieve here, which is when you have all blues here, and you just have a single red, well, then that red is super happy, because it can just tunnel freely in this lattice without any energy cost. So you start seeing, at some level, given by the filling of these excess fermions, it becomes actually nice for the doublon to surround itself with a bunch of these excess fermions. So it's actually interesting that this correlator turns around and becomes positive, and I think that's a very interesting point where you would like to search for things like FFLO, because now these excess fermions could actually like to sit sort of in an ordered way in between these doublons in a nice sort of fashion. By the way, this is actually just the attractive version of the TJ model with, however, density-dependent tunneling. Steve White is, I think, here and points out that it's important. We cannot neglect the density-dependent tunneling. So in the next talk, you will hear by Chun Han about the theoretical calculation. So we threw this data. We just submitted it to Flatiron Institute. What happens then is amazing theories happening, and they could reproduce these data. And what I was extremely happy about is to see that they could really, totally within error bar, see that the correlator of the doublons and the singlons indeed crosses, in this case, 1, meaning that the excess fermions now love to sit next to the doublons. Just to maybe summarize what type of crossover we are seeing, you can look at the density-density correlator at 1-1 distance. That's sort of the thing that's sensitive to a charge density wave ordering. And you see at low density, you don't have much of that charge density wave order. And at high density, you start actually having it. So this is sort of a nice indicator for when are you forming a sort of a ordered Bose gas versus not. And this is doing this correlator versus density and magnetization from our images, and you can get some sort of idea that yes, over here, near half filling, you're not surprised to see charge density wave correlations. And of course, it's also sort of clear if you go away in terms of magnetization, it will also tend to weaken this charge density wave, but to be explored further. And you can also look at the fermionic nature of these excess fermions. You can ask, are these excess fermions fermionic? I mean, do they have a nice Pauli hole or not? And for large magnetization, when you have basically a gas of these excess fermions, yes, they have a Pauli hole. There is a total suppression of the probability to find another excess fermion near you, if you're an excess fermion. But at low magnetization, you don't see this. You see a positive correlation because those excess fermions are actually still part of pairs. Yeah. So there's also kind of a crossover which goes through 0, giving us another type of correlation diagram, which actually works very well together also with simulations by Ehsan Khatami at a little bit more elevated temperatures. So this is kind of a robust signature. And summarizing, this gives then the, well, don't want to call it phase diagram, but correlation diagram for the gas from the experiment, where here we had the idea there should be a phase where we have non-local bosons swimming around uncorrelated. There should be a charge density type phase, which at low temperatures becomes a superfluid. And over here, for large magnetization, I should have, on the one hand, a charge density wave sprinkled now with spin, so these excess fermions that might also order, and that could be sort of the dual or the cousin of the FFLO order that you expect away from half filling over here. I put a question mark because who knows? And of course, at low density, large magnetization, it's going to be a Fermi liquid. If you want a Bose Fermi liquid. Good, so we already saw there are lots of exciting things to do with cold atom simulators. We have novel systems coming online, triangular. We heard a lot about non-local interactions from Rydberg, Wasim's group, or molecules, also Wasim's group. That's bosons though. But you know, we're very excited to look at all these new knobs that one can attach to these systems. Okay, with that, I thank you for your attention and the group for the amazing work.
Thank you, Martin. There's been a lot of questions. More?
Yes, so great work. You know, you described this nice mapping, and you showed many results. So I want to just keep a little bit of an overview. Because many of the things you measure, we can equally do in the repulsive model, but there are some cases, right, where you cannot do it. Like I think you mentioned with the the picture you gave for the superfluid is great, right? Because if you do coherent spin flips, that's like coherently creating a pair, right? You cannot do that on the repulsive side.
It perfectly maps. In the square Hubbard model, it perfectly maps.
Yeah, right, but if, experimentally you cannot do it, right? You cannot have...
That's a very nice point. So while theoretically there's this beautiful mapping, experimentally it's actually kind of two different things. And some things that are easy on one side are hard on the other side. For example, on the repulsive Hubbard model, I can just play with my RF drive and turn an a Z interferometer into an X interferometer, no problem. How do I do this on the attractive side? I have no idea. If you can tell me, that would be great. Like, you'd start with a charge density wave. What do you do to make a superfluid? You would have to have a two-particle operator, right? Because you need to suddenly like make it. So I have some thoughts, but it's absolutely harder, right? And similarly, polarons. If you look at magnetic polarons spectroscopically, it might actually be easier for some quantities to look at the polaron that we have swimming in this charge density soup, because it's a real particle. It's not a hole. So it's sometimes easier to make a spectroscopy on a particle than on a hole. and so if we look at the spectra of the synglons in the charge density wave, we might have hopes to see the character of this polaron maybe more easily on the attractive side than on the repulsive side.
Yes.
No, maybe. No.
I think that's a great direction to explore, right? You know, push the frontiers. Some things you can do on one side that you really cannot. Yeah.
Right. Very good point.
Once you go to multiband systems, you destroy this mapping entirely.
Yes.
And you kind of alluded to the fact that this is a direction which might be interesting for simulators because of our understanding of goop rates. How do you now think about, you know, which side opens up what directions? And
this is a super good question. I actually think it's just doubly rich then. So, for example, the triangular lattice is fantastic already. The mapping breaks down. It only works when you have a bipartite lattice.
Yeah.
And so triangular is already great, and there should be something else happening on the attractive side of things. I actually haven't thought about what will happen, but it's not a mapped version.
Right.
So that's very interesting. Also, if we switch on T prime, things go to hell, because now it's not a bipartite lattice anymore. Now we actually connect these lattices. So all these things become very interesting. And it's just a wonderful opportunity just to explore. And it becomes sort of doubly rich as you do this, away from this point where they make contact. So it's kind of nice. Yeah.
So, Martin, when you talked about correlations between synglons, you said that they repel each other. And if they are to make a follow phase, they should make stripe-like objects. Mm-hmm. And when people were on the repulsive side, they start seeing these incommensurate peaks, large enough doping, which means in your case would be large enough magnetization. Yeah. So is it that in this case temperature is higher, and so you do not yet see this tendency towards at least some kind of bunching of singles to make a follow-type reverse of magnetization?
Yeah, I mean, one should also say we haven't taken enough data to meaningfully extract those longer range correlators to maybe see whether already our temperatures there. Our temperatures are not hotter than what's done elsewhere. We have like a 0.3 or something T, so they should be there. So it's interesting to explore whether we see a glimpse of stripes maybe. Very interesting. Thierry, I think you had a.
So maybe a comment on the mapping to go absolutely in the direction you mentioned. Initially, when we thought about this was because the attractive seems to be a little bit more stable than the repulsive. So, but with a microscope, it's pretty clear that with the ability to measure densities, it gives a super strong boost to measuring superconducting correlation, because to the best of my knowledge, and correct me if I'm wrong, there is no direct way to measure superconducting order. People measured pairing, the gap, but to know if something is coherent, except for bosons where you measure the narrowness of the central peak, for fermions, I'm not aware of any measurement that would measure directly if there is superconducting order in a system. So a good way is to go to the other side and then measure some density or spin density correlation, and bingo, you're set.
Well, one could hope to measure heat transport and observe second sound.
Point taken, but today there
Not
is
today.
no measurement.
Yeah, but yeah.
That was my question. Have you already thought about if that's feasible in your system?
Oh
to
yes,
do
absolutely.
that?
Absolutely, it's actually easier than in the unitary gas. You just look at, for example, the density of broken pairs or stuff like that. There are tricks how we can actually sort of project out those loners that have not found a partner and then watch them run around. So that should be straightforward. Botant has to do it, so I say it's easy.
Thanks, Martin.
Thanks.